Welcome everyone to the Inside Track. Our session today is Impact Imaging, exploring the cutting edge of ultrasound technology with Brian Anthony. Brian wears many hats at MIT. He's a principal research scientist whose academic homes are in the Department of Mechanical Engineering and the Institute for Medical Engineering and Science, IMES, as well as the Clinical Research Center, which focuses on health and wellness. He's also the associate director of MIT.nano, with a particular affinity for the immersion lab and the data side of nanotechnology. And he's a faculty lead for the MechE Alliance, which builds connections with industry, both for education and research purposes. With that, Brian, what can you tell us about the latest innovations in ultrasound technology?
Siobhan, thank you for the introduction. And good morning, good evening, good afternoon, everybody, depending on where you're joining us in the world. So I'm joining you virtually from two places at MIT. MIT.nano, the Immersion Lab, is an MIT central facility. It's open to the MIT community and outside users, heavily instrumented, that allows the human to be the specimen and instrument, and the Immersion Lab is that instrument, enabling immersive technologies and new modalities of interacting with data and the world. And similarly, the Clinical Research Center at MIT is another MIT central facility, again, open to the MIT community and outside users, broadly supporting human subjects research at MIT and in our collaborative partners, industry and academia. So together, these central facilities allow us to be very innovative at MIT in developing sensors, developing methodologies to get better data. So first, I want to tell you three stories. Handheld large volume imaging. Ultrasound imaging in its conventional way, when you're holding an ultrasound probe, suffers, if you will, from variability. It suffers from the variability associated with patient motion or doctor motion. Or if I want to track a tumor or an object over time, how do I know that the image that I acquire today and the image that I acquire a month from today and 6 months from today is at the same location on the body, acquired in the same way? And the answer is you don't. So we're addressing this problem of variability by augmenting the imaging process. One example is we'll add cameras to the outside of the ultrasound probe, and we solve the problem that Google solves when they drive cars around through the world. With one camera, or with more to make it easier, we will simultaneously map out the world, where the world is the patient. So the camera attached to the ultrasound probe is acquiring imagery of the skin or of things right below the skin. And the ultrasound probe is acquiring these slices inside of the body. We'll use these together to create dimensionally accurate volumes analogous to what you can see with MR or CT. So some of the imagery that we're seeing here on the upper left is a conventional ultrasound image. I believe this is a slice maybe taken through the liver. The upper right and central image is that of the skin. The central one is the microreliefs of the skin, and the upper right is the vasculature. These are seen with the camera. On the left, the ultrasound image is seen with the probe. We take this combined imaging system, so cameras and ultrasound probes, and we slide them along the body, mapping out the world and stitching together in a dimensionally accurate way these singular two-dimensional images that are either properties or structure, such that we can create a full whole organ volume of, this case, the liver. This video shows you a little bit of the behind the scenes of how this data is acquired. We're sliding along the body. A probe can be scanned in a number of different ways. We create this map of the world, of the external aspects of the body, and then stitch together in a dimensionally accurate way the ultrasound slices, so that now we have a volume interpretation of what's going on in the body, and not just a singular slice, and dimensionally accurate volumes. So taken together, combining skin images, ultrasound images, the algorithms that are used for mobile robotics to create a dimensionally accurate whole organ view with a fundamentally safe imaging modality, ultrasound, to get structure analogous to what you would see in MR or CT. One of the real exciting sort of switches, if you will, is that same technology that we use that was motivated by solving a real problem of variability in medical imaging, we can now apply to things like inspection of fuselage, where an inspector may be going around looking at sections of an aircraft and wanting to know, to map out, are there defects, are there cracks that are growing over time, and to monitor those over time. Combining a handheld magnetic sensor with a camera that looks at the external structure, we can create the volumes that give us a volume view below the surface. So this way we acquire volumes in a handheld instrument. Another theme, let's stick with the theme for volume imaging. And instead of doing it in a handheld way, but let's stick with the low cost and very targeted use, is looking at conventional ultrasound systems on a gantry system, on a robotic system, to again acquire volumes. The application that motivates this research in particular is prosthetic fitting. If you are wearing a shoe and walking, you know that if the shoe does not fit well, it doesn't take long before you have a blister and are very uncomfortable. That problem is magnified by an order of 10 if you're an amputee and require a residual limb. So how can we make it so that we make a perfect custom fit of the sock or of the shoe that attaches to the subject? Here, we've developed a system that is a low-cost reuse of a conventional ultrasound imager that we put into a water tank along with the patient's residual limb. And we scan this camera or this ultrasound probe around the limb. But to make it low cost, we want to use a conventional system. To make it comfortable, we don't want to constrain the patient. And so the patient may be moving. We allow now an integration of an ultrasound imager and a camera. We put a three-dimensional camera in the bottom of the tank that tracks the limb motion as it's moving around while the ultrasound probe is flying around. So let me show you what that flying around looks like. Here is the system in practice during a human subject study in the Clinical Research Center at MIT. The ultrasound probe is flying around. We see, maybe if you look at the bottom of the tank, you can see the camera looking up at tracking the subtle motions of the limb. We combine all that data and we can construct volumes that are very analogous to the volumes that you would acquire with a much more expensive, much more time-consuming imaging modality, such as MR. We take that imagery together, and from that ultrasound data, we can do two things. We extract both the geometry of tissue, of the external aspects of the tissue and of the bone interfaces, but we're also able to extract the tissue properties, the elasticities, the stiffness of the tissue. Taking that data in collaboration with Hugh Hare, for example, at the Media Lab, we then can design a custom socket that is 3D printed based on the properties of the patient. We create a 3D socket that is stiff where it needs to be, soft where it needs to be, and it's a perfect geometrical fit. And that serves this purpose of making a custom low-cost way of developing this perfect match of the shoe or the sock to the amputee. Now that same technology, this idea of scanning around a volume and in taking that data and estimating the structure and properties, we're also applying that same technology to imaging of pipes, whether it be for oil delivery, so a mix of water and oil, but a low-cost imager, or in this case, an array of imagers around the pipe, can allow us to track in real time as stuff is flowing through the pipe, the mix of water and fluid of particulate. And again, motivating originally by a medical application, but the technology solving a real problem there and a need is now being repurposed looking at manufacturing technologies. So the last quick story that I want to tell you, turn it over to Siobhan after that and you for questions, is in laser ultrasound, or how we can image at a distance with sound. For decades, laser ultrasound has been used for non-destructive testing, meaning we can take light and use it to shine it on an object and create sound in that object. So here we're looking at a silicon wafer. The silicon wafer, for example, will undergo rapid thermal processing. And during that processing, temperature is changed and chemicals are flowing over the silicon to change the properties of the silicon. We would like to know the temperature of the silicon. We'd like to know if there are defects in the silicon, but we can't touch it. And we're looking at the wafer through a window. This is appropriate for silicon. It's also appropriate for forming of metals or aluminum or steel. I want to take now a non-contact way to interrogate with sound. So here we use two lasers. One laser is a pulsed laser. So analogous if you turn your flashlight on and off real quick. We take that pulsed laser, we pass it through a conical lens and we form a ring. And this ring of light is pulsating onto the surface of this case silicon. Locally, where that light falls, it very locally heats up the wafer, heats up the material. That heating creates a stress gradient. That stress gradient then needs to propagate. It propagates as sound. So with light, we've banged on the material surface and generated sound. Then we'd listen to that sound. We take a continuous wave laser, shine it at the center point of this ring, right? And with an interferometric technique, we can detect the vibrations of the skin surface. We receive that sound wave with light, not contacting, purely with light, and we can back out the elastic constants and the properties of the silicon or the defects in the material. Now, the exciting thing is, if you then pick an eye and skin safe laser, you can do that same phenomena on people. We had a paper out in Nature 2 years ago now, where we take 2 laser beams and shine them on the person's body, scanning them across the body. Again, relying on this effect, a light going on and off will create a sound wave in the body. We use a second laser, listening to the sound at a distance, so that we can shine that light, scan it across the body. Light falls on the surface, sound propagates into the tissue, sound propagates back out to the surface, and light then detects vibrations at the surface. We scan those across the body, and we can create a laser ultrasound image that was acquired 2 meters away from the person. And here we're showing back to the original aspects of the story, that non-contact laser ultrasound image side to side with what you would acquire at the same location on the body with a handheld ultrasound probe. So I just wanted to share with you sort of 3 little stories in imaging, what's possible, uniquely enabled by the central facilities that we have at MIT, both the MIT.nano Immersion Lab and the Clinical Research Center. And Siobhan, thank you for the introduction. Happy to take questions from you and from the audience.
Thank you, Brian. Fascinating. It's interesting to see the evolution from the conventional contact ultrasound technology, where you're augmenting and automating to some degree to get, I guess, improving not only diagnostic capacity, but also improving workflow, I would imagine. And then, breaking the paradigm to going to non-contact laser ultrasound. What do you see as perhaps the most compelling or a couple key applications of the non-contact laser ultrasound?
I think there are many. Certainly as we're working to address the issues of variation in ultrasound imaging, eliminating the contact eliminates the patient or the doctor motion and the variable pressure that may happen between the patient and the doctor. But another very exciting area is if you would like to image in a fundamentally safe way, so not ionizing, not radiation, it's a tissue that's been damaged, whether it be burned or tissue that you can't really easily access during a surgical procedure. So being able to integrate either on the battlefield or for a burn victim or in the surgical suite, sort of imaging modalities that can be that third arm to image the patient internally, I think are several of the exciting areas that I think will be uniquely enabled by these technologies. Right.
That sounds promising indeed. So a question from the audience regarding the robotic use of ultrasound technology in the water tank for prosthetic modeling. Does the water tank help with getting more angles? What's the advantage there?
Yeah, so the benefit of the water tank with conventional ultrasound, when we're imaging with megahertz of frequencies that don't propagate through the air. So if you're using conventional ultrasound, you need to use gel to make a contact between the probe and the patient. Here, the water is serving as the basis between the contact between probe and patient. But the other thing the water is doing is eliminating the need to contact and locally deforming the tissue. Because what we would like is an undistorted and unperturbed image of the geometry of the external tissue of the residual limb, the distances between that external tissue and the bone. And if you were making contact, then you naturally introduce aberrations and defects that are possible to correct for, but it's far easier to make a robust system that doesn't ever need to deal with those issues of error.
Right. And then with the laser non-contact ultrasound, I mean, you've been working with lasers for most of your career. And one of our questions from Shannon is, can you describe more about how you got here? Maybe what worked, what didn't, how iteration based on personal fit improvements, so forth and so on. Like what's your trajectory been, and what have you seen maybe along the way that's really surprised you about the technology as it advances?
A technology in particular for ultrasound broadly, or laser ultrasound in particular?
Well, maybe laser, I guess.
Okay. Well, I think one of the lasers have been used for such imaging for decades, in non-destructive testing. And one of the exciting things that's happening now, and this was done in collaboration with folks at Lincoln Labs and on campus here, is the miniaturization of optics and light. So the same way that we're able to miniaturize electronics to make our cell phones and our earbuds, integrated photonics is using the same technology stack, the same design tools, the same fabrication technologies, the same materials, to take big lasers, big detectors, and put them on small chips. That need, or the need that's motivating those optical integrated photonics innovations, are things like the data center. Light is a much faster, low lossy way to communicate across distributed cores, but also self-driving cars. So LiDAR as one motivating use. So those are big market technologies or needs that are driving the innovations in integrated photonics that are small receivers, detectors, transmitters, ways of propagating light on substrates that give us the feasibility of taking these systems that had historically been only realizable in the factory or in a big lab, and actually putting them into a handheld device, or a device that easily fits in the surgical suite.
And how far along are some of these technologies? So with the laser non-contact ultrasound, and also the for imaging for prosthetic limbs, Matt asks, is it already en route to organizations? When are these things going to market, and when can we take advantage of them?
Yeah. It's a big question, and it's a long answer. It depends on what we're trying to do. Generally speaking, I think many at MIT will quote the fact that it takes 15 to 20 years for an innovation to get out of the lab into the marketplace. We're benefiting, though, from a long history in ultrasound and new innovations that are happening. And so for things like the prosthetic fitting, which is a novel reconstruction of conventional imaging, that's commercially ready now. It's not deployed yet, but it's commercially ready. It's not, the imaging tools don't need to be created. The fitting process, and there is a company I know that's spun out of the Media Lab that's looking to license both the imaging techniques and the modeling techniques that allow us to take that image data and create the fit. The real innovation that needs to happen for the prosthetic fitting is the detailed understanding of what are the appropriate modifications once you have a model of the limb. Do you exactly want a conformal fit, or where do you need it to be tight? Where do you need it to be snug? And so those are some of the things that need to really be used to get that aspect out into the world. But the imaging solution is available now. That's a thing that if there were a market and a demand, it's low cost enough that it's achievable now. On the laser side, I think to make it fully deployable, there needs yet to be some enhancements in terms of both the miniaturization of for large deployment. There needs to be further miniaturization of the laser sources and the detectors. But for things that, if there were a high value use, like in the surgical suite or for military applications, it's not there yet. But I think the time is probably 10 years away, 5 years away, and a little less than 20.
And it makes me think about the just sort of, you mentioned industry and some of the collaborations that need to happen. And in your research, you have industrial partners, and you have partners in clinical settings in hospitals, and then you bring those together with the MIT research aspect. Can you talk a bit about how it is such a collaborative venture?
I think one of the exciting things about working closely with both MIT.nano and the Immersion Lab and the Clinical Research Center is those are central facilities that are available to the community. And that community is both the on-campus community and external partners that may want to come in through research collaboration, work with us, or for solving their own independent needs. In the healthcare region, in the healthcare environment around Boston, we're blessed with density of Mass General Hospital, Brigham and Williams Hospital, Children's Hospital. where it's a 5-minute walk away, and we can work with the clinical collaborators to understand the needs and the motivations and to get into the clinical environment. And for the things that aren't appropriate to put into the hospital, we have the clinical research center that allows us to reconfigure and have either home-like or hospital-like environments where we can pilot technologies on campus, bringing the doctors to us. And then in the immersion lab, it gives us this full instrument, the room, that allows us to do motion capture of objects and of people, and to just display the data at the human scale and to interact with it and understand it in a way that's far more organic than staring at your screen, either in front of the little device or on the big screen. So long-winded answer to your question, but it's the ecosystem around Boston. We're blessed, and it's very fortunate to be able to work with external partners that know how to translate technology and that come with both challenges and opportunities.
Yeah, it sounds like a nice collaborative nexus. I was interested in the Nature paper, which the title is Full Non-Contact Laser Ultrasound First Human Data. The first human data part being key. That you had to go by this committee, and it's such a big step. Is it, now that you've gone past that step, does that sort of smooth the way for the advancements to come in bringing that technology forward, or is it sort of a continuing, you have to go back and get approval for protocols again and again?
Well, certainly for, I guess there's a couple aspects to that question. Anytime you're trying to innovate in medicine, you need evidence. Whether you're an academic researcher or a commercial researcher, you need to collect data, you need to publish, you need to demonstrate how the technology works, making that open and available to the world. Okay, so that's an important aspect, whether you're an industrial or an academic researcher. But when you're doing human subjects work, you want to make sure that you're protecting the privacy of the volunteers or the patients that are enrolled in the study. You need to make sure that things are fundamentally safe. So CUIs at MIT, that's our institutional review board, will review protocols or things that you want to do and make sure that what you're doing is safe. They'll say, hey, let's make sure that the laser energy that you're delivering truly is eye and skin safe. And there may be paper analyses that need to be done or experiments that need to be done to verify that that's working. And the data you're collecting, are you potentially revealing anything about the human, about the subject that should not be made available, that it's confidential and private information? So those types of protocols are important to ensure the safety of the process of the subject involved, the validity and veracity of what you're doing, to collect that body of evidence that demonstrates that, hey, this thing doesn't just work on one person, but on multiple. So it's always, you need to continue to do your research. You need, in the commercial clinical space and medical technologies, whether it be devices or algorithms or pharmaceuticals, you will always be collecting more data to demonstrate that what you're doing is safe and effective. And things like the institutional review board help to keep that running smoothly.
Right. And what are you most excited about going forward? What's next on your agenda?
Yeah. Well, if you couldn't tell from my talk, I very much like this sort of interplay between manufacturing on one side and medical on the other. And one of the really exciting things about certainly the collaborations between the Immersion Lab and the Clinical Research Center is the way to interact with data. I will describe the Immersion Lab as the data interface to nanotechnology. It allows us to take big data, big volumes of data that are at the scale of Mars, for example, and bring them down to the human scale, whether that be on headsets or in wall-mounted displays, but to interact with that data the way that we interact with objects. So we move around, we gesture, and you don't have to just point and click, but you naturally can stream through that data, whether it's big data, big volume data, and made it to human scale, or small data, microscopy data, medical imaging data, that you blow it up to the human scale. But it gives me the opportunity, if I can capture how a person moves around and just put them into the data, I can interact with that synthetic world the same way that I'm gaming. Same AR and VR, artificial reality or augmented reality and virtual reality tools for gaming give us a new way to do research and to understand our data and to explore. So I think it's that intersection of using these tools, these gaming technologies, in our research and education, enabling things like innovations in manufacturing and innovations in medicine are where I sort of spend a lot of time doing work.
And are you constantly on the lookout for sort of these cross-pollinating applications? Are you surprised when they happen, or how do those unfold generally?
I guess I'm not surprised, but I do go out looking for them. But you don't need to look that far. Opportunities like this to speak to a diverse community. Keep your ears and eyes open and your fingers out and open. It's the cross pollinations. Team science of it's mixing a mechanical engineer with a computer scientist with a doctor, where it's hey, have you tried this in this application? Where I think the real innovations in the modern era are enabled. It's that interplay between mechanical engineering and manufacturing and information technology, IoT, big data. These are the places where we're able to leverage that combined multiple discipline space.
Fascinating. Thank you everyone for joining us, and we'll have you back on Thursday to discuss ambient monitoring. So I look forward to that as well.
Very good. Thank you, Siobhan. Thank you, everybody.
Bye.